Good evening, everybody. I hope that everybody can hear me very well. Luxoft is very happy to be host of the first webinar with Christian Mercury and welcome you on the first of its kind edition of webinars dedicated to automotive software. Our IT star today is machine learning architect and backend engineer with Luxoft, working for an auto project, who has 10 plus years of experience on various projects in Google, including the Google Accelerated Science team, advanced numerical methods including statistical learning, time series forecasting, and high-performance computing. Today we will have 45 minutes presentation, and after it, Christian will spend 15 minutes answering your questions. Feel free to use the Q&A section in the bottom of your screens. And after Christian gets your questions, he will be able to reply to each of them. Now I'm passing the floor to Christian, and good luck with presentation.
Okay, yeah. Dear Ilyana, thanks for your kind words. Yeah, dear audience, I'm super happy to speak to you. So let me start to share my screen so we can get started. Okay, dear audience, I hope you can hear me. If there's anything, please try to contact the administrator. Yeah, the title of the talk is like Deep Learning for Automotive. And yeah, I'm working since like a few months for Luxoft, and I work in a dedicated project for the client Nordo. And you see the logo of Nordo in the upper right corner. So Nordo is a startup from Palo Alto, so from the Silicon Valley, and the mission of Nordo is to make driving and transportation easier, safer, and smarter. Well, that's like a huge goal, and in order to work closer to this goal, Nordo has a device that's actually already like deployed in the field, and it's available on the market. And the device is it's an electronic device that's mounted into the vehicle, meaning into the car or potentially into a van. And the device has two cameras. One camera faces the outside of the car, so the scene in front of the car. And the other camera monitors the inside of the vehicle's cabin, like the driver and passengers. Okay, and yeah, within Auto we are working super hard to bring as much intelligence onto the device and into the cloud. So the device is connected to the cloud and sends data to the cloud, but the device also runs deep learning and AI directly on the device while driving. Okay, I don't want to go too much into this, so allow me to give a short overview of what we are going to see. So in this webinar, I want to like share my view of what kind of challenges for deep learning there are in automotive. There might be much more, and there might be way more complicated challenges. I'll try to scratch the surface of this. What I definitely want to do is that I want to introduce the basics of convolutional neural networks, CNN for short, which became, or it is the workhorse tool for deep learning and currently also for computer vision. And parts of the slides that you will see later about computer vision and about cellular neural network, convolutional neural networks, they are taken from the excellent Stanford and MIT courses on computer vision and deep learning. Those courses, be warned, that is material for 10 or 20 or more hours of self-study. But I strongly encourage you, if you are interested in computer vision, to go through those courses. I'm trying to give you a very brief introduction here, okay? So, yeah, let's talk a bit about AI, artificial intelligence for automotive. So, of course, the topic that is now like in the news, that is autonomous driving, right? and autonomous driving, meaning the car is driving itself. Okay, there are actually different levels of autonomy. So it starts from kind of just assistance to the driver, for example, keeping the car in the lane, preventing the car from getting too close to the car in front, keeping the speed, stuff like that. Of course, the holy grail that different companies are like going for is a full autonomy. That means the car is able to drive itself from A to B. No driver is needed. No driver intervention is needed. Basically, it means no person inside the car needs to have driving license. How far we are, how close we are to this goal, I think I don't even know exactly how much we are. Different things are in the news, but I'm not going to go into detail. So, but just to break it down, what are the challenges for autonomous driving? It's of course localization mapping. Like localization means I need to know where the car is. Not only like GPS wise, I need to know where the car is steering to. I need to know the speed. I need to know the gearing and stuff like this. And I need to have a very good understanding where I am and in which like environment I am. That's mapping, right? Mapping meaning like having available super precise map data that tells me where's the street, where are traffic lights and the like. A challenge, of course, is scene understanding. The scene is, of course, what is going out, what's going on outside of the car. This means other vehicles. It means like other participants in the traffic, pedestrians, bicycles, motorbikes, trucks, whatever there's going on, traffic lights, street signs, and the like. Movement planning and something that is actually that people don't think too much of, and that is cabin monitoring. And now you might ask, okay, why? The car is driving from A to B. Why would I need to monitor the cabin? Well, have a look. When there's autonomous driving, the behavior or the usage of driving will change most probably. It could be that we will have much more ride-hailing services like the popular like Lyft or Uber. And so it means different people will be inside the car, not necessarily the owner. There might, cars might be shared and there might be different people inside. And there can be, of course, things going on inside the cabin that are dangerous or threats, or people can, people can have health problems. So it is actually important to monitor the cabin, right? Okay. So another, like if we don't go for the fully autonomous driving, we will still have the, let's call it a use case of the assisted driving. And in this use case, the driver is still in control to a certain extent, potentially is driving the car is fully, or is like just taking over control in certain situations when the AI is not sure what to do. In that case, there's still a lot of things that we can do. This is, for example, to warn and to inform the driver about dangers on the street, tailgating, like driving too close to the car in front, potentially other cars changing the lane, unexpected like objects moving into the driveway and stuff like this. And the challenges are actually very similar to the challenges for the fully autonomous driving. It is scene understanding. Scene understanding means the car needs to understand what is going on outside of the car. And again, and this is also very similar, it's monitoring the driver's state, the emotional state, like is the driver stressed? I'm not talking about is the driver in love, but is the driver super stressed? Is the driver distracted? We see it in the upper right corner, for example, of course, like texting on the smartphone, or in general, like talking to other passengers in the car, or in general being distracted. And distracting is super dangerous. Like just a few seconds not focusing on the street means you traveled a couple or dozens of meters, like in kind of a blind mode, right? And also like giving the demographics in the Western like countries and Japan, people are in general becoming older. fortunately usually at good health, but still we have the situation that people inside the car, driving a car, controlling the car, can have a health incident, a stroke or whatever that actually like renders them unable to continue to drive or even to control the car or bring the car to a controlled stop. Okay, so this being said, most of the challenges I described, I would classify them as computer vision-like challenges. So computer vision is a big thing for automotive. There are other artificial intelligence challenges, and there is not only, let's say, the optical image like that you do vision on. It can be LiDAR, it can be radar. But for this presentation, I would like to focus on computer vision. And we see here a few examples, like, for example, scene understanding. I need to know other vehicles. I need to detect vehicles. I need to localize those vehicles. I need to know where I am relative to those vehicles, right? Pedestrian and cyclist. Is a pedestrian, like in the lower image, is a pedestrian crossing the zebra crossing. Traffic lights, I don't want to run a red light. Like if I'm an autonomous car, I need to know what's going on. Maybe in the future, the traffic light will send a Wi-Fi or whatever signal to the car, but currently all the signaling is optical, right? So in general, scene segmentation, meaning vehicle detection and lane detection, is a super important thingy. And again, also driver and cabin monitoring is a computer vision problem, okay? For example, also think about it, if you have a shared car, you might want to have a mechanism to identify the driver. Well, the driver, maybe there is no driver, so you want to identify the passenger, and the passenger may not have a key or something like that, right? So you don't necessarily have a signal that helps you to know who is driving. So face identification is actually an important topic here. Okay, so computer vision, it's a topic that is in research for, I don't know, like several decades, right? And it's actually a super hard problem. For humans, it looks easy, like, you know, like vision is one of our like strongest senses, like the sense also we rely extremely much on. And it seems for us to be super easy to detect the same object under different conditions, light illumination conditions, different viewpoints. We have no problem to detect in the upper right a cat like hidden behind a piece of a wall, or even like in the background clutter, like to see the cat that actually has a very similar like pattern like the background. It seems to be super easy for us, but think about the optical system in living beings developed over millions of years. So it's actually not that easy. And I try to describe why this is not so easy. Okay, let's pretend we are a computer. So on the left side, we see a cat. Like I said, a cat, it's super easy to recognize, right? And now we focus on that patch that is like in the below the head of the cat, like in the black frame. Okay, and what the computer sees is a grid of numbers, and each of that number is between 0 and 255. And basically, the higher the number, the more bright is that pixel. Like every number is a pixel. And actually, it might be not only one number, it might be three numbers. One number means a grayscale image. Three numbers means we have a color image with red, green, and blue. So three channels, one channel, one number telling how much red is in that pixel, one number telling how much green is in that pixel, and one number telling us how much blue part is in that pixel. That at least is enough to describe colors for humans. It's of course not the full spectrum that's maybe given, but humans seem to be able to cope with three colors very much. Actually, like humans, not every human sees the same. There are people that are colorblind that can see actually just a restricted set of colors, and there are people that even see more colors than others. Apparently, there are some mutations where you have like even more fine-grained color vision. the funny thing is that all of them seem to be able to drive a car. So color seems not to be the most important thing when it comes about driving. Okay, so have a look now. Sorry, I'm switching back to this slide. The computer sees like, you know, a grid of numbers, actually quite a lot, right? Even in a low resolution channel, in a low resolution image, we have 800 by 600 pixels. And for each pixel we have 3 values. So this is like 100,000 values, right? Like in the order of 100,000 or even mega. Millions of values. So if you take a modern camera, you have 60 megapixel, and each pixel has at least 3 bytes. So that's already a really huge number, a really huge amount of information in a single image. Okay, but now you could say, well, I could just compare those numbers to some predefined set of numbers, and I know it's a cat. Well, no, it turns out you can't. Like, imagine. Here in this slide on the left side, we see the camera, and imagine the camera is rotating around the cat. And even if the camera does a slight movement, the values in the grid, the numbers, the values in the grid that we see will change. And they will change in a very, let's say, not obvious way. Like just, you know, imagine the camera rotates around the cat. It will see it from different angle. There will be different light, you know, illumination. So all those pixels move. There's not an easy way of comparing those numbers to something that we know, right? And actually this explained why for super many years it was super difficult. It was a challenge to recognize or identify objects in an image. Okay, and because it was so difficult, people were like, how to say, they were thinking like, okay, we have to provide a data set for research that allows people to train their models, their algorithms on, and so they can easily see how good they are, and they do not need to spend too much time on collecting those data. So that was the start of the so-called ImageNet. And ImageNet is a data set of more than 14 million images. And the images are out of more than 21,000 categories. And the categories are hierarchical, so these are not all totally different. So, for example, let's look at a high-level category, that's fruit. People, you know, we have an idea what's fruit, like apple, bananas, kiwi, mango, and the like. And there are actually, in the ImageNet data set, there are 188,000 images of fruit. And out of this, about 1,200 are Granny Smith apples. Okay, Granny Smith is like this greenish, nice, shiny apple. And you see here just in the lower part of this slide, you see the different images, example images from the ImageNet. And you see that, you know, it's not so super easy. Like you know, you can see just a part of the apple. The colors can change. You can see it like from the bottom, from the side. There's a slice card out of the apple, different backgrounds with shadow, with reflection and the like. Okay, so yeah, it was a very fortunate thing that the community, the computer vision community, came up with this ImageNet data set. Why? Because it's not only a data set, there's also a competition. And the competition is called the ImageNet Large-Scale Visual Recognition Challenge. And the challenge was held every year since 2010, if I remember right. And it's kind of a competition, so different groups give package their model, their algorithms, and they are like judged. There's like a leaderboard, and who's like, you know, whose algorithm is doing the best, right? Is performing the best. And performing the best means it recognizes the objects with the highest precision or the lowest error, which is the same thing. Okay. Well, here we see now a list of models. They are called networks for a certain reason, but let's go to the next slide and look a bit more on what happened there. So let's focus on the bar chart in the left upper corner. So here we see the classification error of the best performing model in each year. So, like I said, the competition is held year by year, okay? And we see in 2010, the classification error is 28%. 28%, that's a lot. Well, that's, that means like more than 1 out of 4 pictures or images is misclassified. It's kind of bad, right? Why it's bad? Because, humans can do an error of 5%. And now you say, why humans should be perfect? No, well, humans are generally super good classifying, let's say, like apples from bananas or bananas from cars. But in the ImageNet data set, there are also more difficult categories, for example, breeds or dog breeds, right? So birds and actually humans are not that super good in really discriminating between some really close by breeds of dogs, for example, that look super similar, right? Like at least to me. And now the funny thing is, have a look. So the error in 2010 was about 28%. So we would call that bad. Well, I don't want to say bad. It was the best model at that time. And the model was based on, let's say, handcrafted features generated from the image, plus support vector machine classifier. Support vector machines, very good classifiers in general, with a very well understood like properties and a theory behind and nicely fast implementations. But still, we came just to 28%. And then in 2011, it was, I'm not sure if it was a similar model, but I think it was also based on support vector machines. I would need to check this out. And the error went down by 2%. Well, okay, that's something, but, it's for sure, I mean, that's some improvement. But then in 2012, something happened, right? You see the yellow bar means the error went down to 16%. Why? This was the first convolutional neural network, not the first that was ever created, but the first time that such a network was submitted, I think, to ImageNet. And it was the AlexNet. It had 8 layers. We will come into this later. We will discuss layers later. And so the error dropped significantly, right? From 26 to 16, that is something. And actually from 2012, every subsequent year, the error went down. 2013, it went down to 12%. 2014, it went down to 7%. And in 2015, we went down to 3.6%. That is better than a human, right? So actually an amazing improvement. And to make the long story short, these were all neural networks, basically convolutional neural networks. Year by year, those networks became more sophisticated. And finally, we come to an astonishingly low error in 2017. That is like about 2.5%, 2.3%. And of course, in 2018 or end of 2017, there came even better models. I think Google had the AutoML generating some network architecture. So it's actually a neural network architecture that's generated by a neural network, right? That performs amazingly good on this competition. Okay, so long story short, this from 2012, this kind of revival of the neural networks, in particular of the convolutional neural networks, it is called deep learning. Deep meaning here many layers, right? And actually the number of layers went up or increased from 8 layers in 2012 to something like 152 layers for the ResNet residual net in 2015. So and deep you would call like more than 8 or more than 10 layers. That's a deep kind of architecture. Okay. Now let's try to demystify deep learning and neural networks. So deep learning currently means neural networks. It might change at some point of time, but currently it means neural networks.
And neural networks, well, that sounds like the most complicated thing you can imagine, but actually neural networks consist out of super simple calculations. So a neural network is a machine that actually it does two basic operations. The first operation is a dot product, and you should know it from your math classes. A dot product is a super simple thing. You have weights, like here we have three numbers here in the in the bracket and a bias. And we have inputs to the neural network, and that is here -2, +6, and +4. And the dot product is simply, you take the first weight and multiply it with the first input. You take the second weight and multiply it with the second input. And we take the third weight and multiply it with the third input. We add the bias. The bias is not multiplied with any input, so it's just a number by itself. And we add all this up, and then we get an output. And it's super simple, right? So that is the first operation that defines a neuron. It's a dot product. It means you have weights, and the weights are specific to the neuron, and you have inputs, and the inputs change. Usually the inputs change with every image or with every sample that you see. There's a second operation that you can consider a bit more, let's say, sophisticated. It's the so-called nonlinear activation function. So usually you take your output value is simply a number, and you push it through a nonlinear activation function. Okay, let's look at those functions to just see that those functions are actually super simple. So here we see on this slide we see like several nonlinear activation functions. Well, nonlinear means just they are not just as simple as a straight line. Well, they have like they are bent, or they have a kind of, they change the direction. And let's focus on the activation function that is currently the most common and also quite successful activation function. It's the ReLU. It means a rectified linear unit, and it's a super simple function, super simple. So the input value is x, and the output of the ReLU activation function, well, as long as x is below 0, the output of ReLU is 0. And as soon as x becomes positive, larger 0, so in that case, we output x. So that's what we see here in the graph. So whenever x is on the x-axis, as long as it's below 0, the output is 0. If it's positive, we just output the same value. That's all. That's all what a neuron is doing. But the complexity and the power of a neural networks come from the fact that we don't use one neuron. We use millions of neurons. Well, depending on the architecture of the network. But in general, that is of course what kind of makes neural networks a powerful thing. And also what it means you need a lot of computation power to do all those computations, despite the computations are super simple. The computations, let me repeat, it's a dot product. It means we multiply a weight and an input. We add up all those products, and we add a bias. That's our output. We put this output to the activation function, and we have this so-called activation of a neuron. Okay, but if you do it for millions, you need a fast computer. Okay, and the neurons, they are not arranged just in a random fashion. Well, there are such networks, but that's not super common. They are actually organized in layers. And the first layer you call the input layer. And actually here let's focus on the left like diagram. So we see a neural network. It consists of, well, two layers. There's a hidden layer and there's an output layer. The input layer, it's called an input layer, but basically here we input the values from the image. Here we have only three input values. That's of course very little. Like we said, an image has millions of, potentially it has millions of input values, millions of pixels, so millions of values. But for the sake of simplicity, here we have three input values, and we have in the first real neural network layer, we have 4 neurons. These are the 4 circles, the 4 white circles against the blue background. And in order to calculate the activation of this first uppermost neuron, So we take a dot product of the 3 values from our input with the 3 weights that are attached to our neuron here. We add the bias, and then we put it through the activation function, and we get an output here, a number. And the same thing we do for the other neurons. Okay? And now, once we have calculated the activations for all neurons in the hidden layer, in this layer here, in this blue layer, we can go on, we can continue and go to the output layer, and also calculate the activations of those neurons. And this time we take the activations of the hidden layer neurons as the input for the dot products for the neurons of the output layer. And as you see, you can of course add more and more layers to such a construction, right? Like you know, it's the scheme is super simple. So each layer has of course its own set of neuron, and you first need to compute the activations in the previous layer, starting from the first layer that actually looks at the inputs. And from that, once you have calculated the activations of the first layer, you go to the second layer, and so on and so on. Hidden means just that well, you know, hidden layer means it's kind of a, I don't want to say it's an old-fashioned word, but hidden means it's not an output layer, it's not an input layer. So nowadays you just call it layers, okay? And because every neuron is connected to all the other neurons in the previous layer, it's called a fully connected layer. Okay, and when you think that you have a million of input values, and you have potentially thousands of neurons in one layer, you get actually like millions or hundreds of millions of weights for such a fully connected neural network. And actually, those fully connected networks, when applied to to computer vision, didn't work that well. They work to some extent, but not that well. Okay, so that's actually why they became abandoned for at least some period of time. But there was a very clever idea of not connecting the layers fully to the previous layer. So, but to use a more let's skip this slide. To use a more sophisticated approach, and that's actually an approach that is stimulated by the biology. For example, how the cells in the human vision system, how they are connected to each other. And let's start simple. So here on the left side of the slide, we have an image. And the image we depict here as a plane, as a slice, we call it a slice, of size 32 by 32. So that's actually a small fragment of an image, right? So we have 32 by 32 pixels, and we consider this volume, we give it a depth of 3 because, again, 3 channels. This means 1 channel for red, 1 number for red, 1 number for green, 1 number for blue. Okay? So we have here 32 by 3 values, numbers, scalar numbers. Okay? And now we introduce a filter. Okay? And a filter is this thing that is specific to a convolutional neural network or to a convolutional layer. A filter keeps the weights of a convolutional layer. And here we have a 5 by 5 by 3 filter, and we have it by, which means 25, we have 75 values, 5 by 5, 25, by 3, 75. Okay, why 3? Because we need, the input image has 3 channels, so also our filter needs to have a depth of 3. Okay, and now how do we calculate the output of 1 neuron in the output? So basically, imagine we put this filter over our image, and the filter contains the weights of the convolutional neural network, and we multiply when we put the filter, when we put it over our image, over actually a patch of our small image, we multiply the pixel values with the corresponding, with the respective value of the filter at this position. Okay, it's again a kind of a dot product, but see it, imagine it more in this three-dimensional structure, and the output is number. And the dot product goes over 75 dimensions, because again, the filter has 5 by 5 by 3 values, weights here, plus in case one bias which is not multiplied with any of the input pixels. So altogether, the filter is described by 76 weights. Okay, so we get one number. I'll later try to explain more. Now imagine, of course, the filter is smaller than our, the filter is smaller than our image. The filter is 5 by 5 and our image is 32 by 32. So what can we do? We can actually shift that filter stepwise over the image to cover all regions of the image. And every time we do it, we calculate an output, and that means we get an output, we get again an output image, this time of depth 1. Why? Because every dot product just gives one value, and the width and the height of this activation is 28 by 28. Why? It's slow. It's less than the input image, which was 32 by 32. But see, we cannot shift the filter 32 times. We can shift the filter only 28 times in horizontally and vertically, because we hit the edges of our image. Okay, so actually the activation is smaller than the activation image, or whatever we get out is smaller than the input image because of the size of our filter. Okay, and now think we can actually, well, one filter is not so, it's not like doing a lot, but let's use several filters. Okay, actually we can use as many filters as we want, and we would get as many, let's say, outputs, activation outputs as we like. Okay, and let me try to show this on this example, how this calculation looks like. Maybe this was a bit fast. So here we see an example. Let me just move my screen. So on the left side of the slide, you see the input image. You see 3 squares, which are like grayish, right? Which the upper square is, the uppermost square, gray square, represents the red part of the image. Then the middle square represents the green part, and the lower square represents the gray square, represents the blue part, okay? And we have 2 sets of filters. We have 2 sets of filters. The first is called W0 and the second filter is called W1. And also the filter has a depth of 3, because I cannot, we cannot see the numbers if you would like to depict them behind, in a real, it's in the set coordinate, we just like put it here, we put it below each other. So here you see the weights or the values of the filter. And for example, to calculate this output on the right side, this is the output volume. You see that the output is -3. Can you see this? How do we come to the -3? Well, we put this filter, we put filter W0, that is this one. I hope you can see the mouse. We put it on over our input image. Okay, and now we multiply this number with that number. We multiply this value with this rate, with that pixel value. We multiply the -1 with the 0, and so on for the second row and for the third row, and we sum it up. And when we do so basically have a look. We just add up -1 times 2 plus -1 times 2. That's actually -4, but we have a bias element of +1. So we end up at -3, okay? And we do this with the green channel that is represented here, right? This is the green channel of the image. This is the green channel of our filter, okay? And now we shift this, excuse me, we shift this we shift our filter stepwise over the image. Can you see it? So every time we have the same, like for the red part, we use the same filter and we move it over our image, and that's how we get the output. Actually, I was a bit fast because we are also switching the filter once we covered the first image completely. We switch to the second filter. So the output that we see here on the right side in this greenish color, that is the output of the calculation of the first convolutional layer. Okay, but we didn't apply the activation function, the rectified linear unit. Okay. Okay, that being said, a convolutional neural network, short CNN, is a sequence of convolutional layers. Okay, and in between we can do the activation function after we calculated one convolutional step. But sometimes, this happens, but sometimes also people decide not to calculate, not to apply the activation function. Okay, and what you see, what I described here, the image is getting smaller in size, with every step because the kernel cannot shift as many times. You cannot shift the filter as many times over the image that you would get the same number of output values in each dimension. Okay, but we can, for example, do the following. We can use consecutively in the higher layers. We can use more filters, right? So the image or the processed image that we have is shrinking in the horizontal and vertical dimension, but in the depths, it's actually increasing. And of course, already when we are here after the first convolutional layer, we have a depth of 6, and that is already not red, green, blue. That is, that those 6 channels are, well, features, I would say. It's difficult to tell what they represent. Okay. And that's what you see. You can do this like 8 times. You can do it 150 times, right? Actually, in this case, you cannot do it 150 times because your image would shrink down. Okay. So there are different tricks to work around that. Okay. Now let's see what can a kernel do, right? Just to get an idea. So here on the left side, we have an input image of an animal. I don't even know exactly what it is. And here we have a 3x3 filter, or kernel, sometimes it's called, it's filter. And this filter is super easy. It has a 0 in the middle element, and all the elements on the outside, they are 0. And if you apply this filter to the input image, you get just the same image out. It's the identity, minus that we lose the, let's say, the row and one line of pixels at the border, the image border. Okay, but now let's use more. Let's go to more interesting filters. So if we put the middle element to 0, but we put the edge elements to 1 and -1, we get an edge detector. I don't know if you can see this. It's a bit hidden on my screen, but you see just I would say, the contours of the face of the animal, right? And actually, this is a directed edge detector. And let's go to the second example where we have -4 in the middle, and we have ones on the top, left, right, and bottom. And this is a different type of edge detector. And going to the and actually kind of I think the most like strongest edge detection is happening with the filter that we see below, where we have an 8 in the middle, and then we have -1s everywhere. And when we look at the output image, I would say, yeah, it looks a bit like artistic version of the input image, with just the structures of the outline of the face, and the most significant lines in the face of the animal are highlighted. Fun thing, calculated that filter has an average, the average rate is 0. So that's kind of, it makes sense because, we don't want to amplify the image, or we don't want to if you would apply this to a uniformly gray image, the output would be 0. That's exactly what I would expect from edge detection, right? Okay, and now let's let's kind of have a look what the layers of a convolutional networks are doing. And it looks like this, that that's a bit heuristically, that the first layer is actually looking at very low-level features that can be found in the input images that we train on. I'm not talking in this presentation about training because it would take us way too long time to go into all the details. Okay. And if you go to the higher level, to higher layers that are more far from the input image, we see that they start to represent more and more complex parts or features of the image. So if you go to the third layer, and I think this network was trained on to detect faces, you can see kind of like schemes of faces, or I don't want to say prototypes of faces of humans. And the funny thing is that neural networks, well, like I said, they are trained on a data set. How this is done, yeah, it's part for another lecture. They learn the statistics of the input data, and the funny thing is that they seem to organize the information they learn in, I don't want to say it's not a hierarchical way, but in a kind of a constructive way that goes from lower level to more complex features. And there's nothing that we actually put into the training that tells the network to do so while learning. Okay? And I think I have to give you one more elementary operation of a convolutional neural network, and that is the so-called pooling. Pooling has no weights. There's nothing to adjust during the training, but pooling does the following, at least if it's pooling 2 by 2, it reduces the size of the image or the activation that we have by 2. So what we do is, it's called max pooling, and have a look at our input image on the left side, it's 4 by 4, and we divide it into 4 squares. Each square is 2 by 2 pixel. And within each square, here's a reddish square, we take the maximum value. So the values here in the reddish square is 1, 1, 5, and 6. So the maximum value is 6. So we write to the output 6. Now we go to the upper right, 2 by 2 square. The values are 2, 4, 7, 8. Maximum is 8. You put it here. And so on. So here the maximum is 3. And for this bluish one, the maximum is 4. Okay, so what does pooling do? It reduces the size of the activation volume. Here you can see it. It was 224 by 224, and it was 64 channels deep. And we pool it, and we end up at 112 by 112. But we keep the same number of channels because we do the pooling actually per channel. So we are not mixing in between channels. Okay. Yeah. And now coming. I think. Let me check the time. Yeah. So I'm trying to kind of give a very rough outline of how convolutional neural networks for different domains or for different tasks work. Different tasks can be image classification, it can be image captioning, it can be image segmentation, or also like object detection in a network. These are different tasks. Image classification means I have one item in the image and I want to tell what is the item. When I segment the image, I might have many, or let's say image segmentation would mean I want to say, well, that part is a tree, that part is a building, that part of the image is a street, and that part is a car. In object detection, I want to tell, well, there are 3 people and a dog on a beach, you know, and they are playing with a ball and whatever. So these are actually quite different tasks with different difficulty and also different architectures, but all those applications have a very common part, at least at the beginning, at the beginning of the network that is used. It starts with the image. It starts usually with several convolutional layers plus the nonlinear activation function combined with max pooling, right? And this is repeated several times. In detail, this depends very much on what we are doing. And after n layers, then comes the different, we call it a head of the neural network that is task specific. But still, it is kind of interesting that there is so much versatility in this idea of having the convolutional layers in sequence, like a repeated sequence of convolutional layers, potentially with max pooling, potentially with other stuff. And then only in the end we kind of like do a more task specific like architecture. Okay, so here one quick slide. Object detection means actually we ask the model not only to tell us what they see, but also where they see it in the image and what it is. And for example, here we see the image where the algorithm detects, well, I would say 2 cows and a wooden pole for a fence or something like that. And you see here the rectangles, these are bounding boxes. So for example, there's the RCNN and faster RCNN that proposes regions and then calculates the object, how sure it is that there's an object in this region. And then actually it outputs bounding boxes plus how sure it is that there's an object and potentially what type of object there is. And there are different like architectures that can do it in one run. YOLO, you look only once, or SSD, single shot detectors. I don't have time. I mean, this would take hours to go into all of these architectures. But it is super, CNNs are a super versatile tool that are used for computer vision. Actually, they are used even outside of computer vision. WaveNet for time series like speech recognition and speech synthesis is also using convolutional neural networks. So it's a super versatile tool. Okay, and yeah, having said that, I think we are coming to the end of this presentation. Thank you for attention. I hope I didn't bore you too much. Yeah, let's maybe start with question and answers. I'm opening questions, but I don't see any questions. Well, there's a question. Okay. So Krzysztof asks, could you say something more about the application of deep learning to the problems mentioned in the beginning? For example, how to detect that a driver is distracted? That's a super good question. Of course, what you do is kind of you will start with generating or assembling a training data set. And you will apply different neural network architectures to say if someone is distracted. What is difficult is to have a training data set of true positives when the driver is distracted and when not. And you need to think about different illuminations, especially in the situation of a car. Light is a very, very bad thing. You can have like super hard sunlight, direct sunlight, where part of the driver's face, for example, is in shadow. Or you can have like the night situation where the image is totally different. I don't want to go into too much detail which type of networks you would use, but basically this would all be based on very similar architectures as I described before. Which one exactly you would use, it's not clear and depends really also on, it's currently under research. Okay. Second question, what is the recommended computing power to recognize the scene outside? That is a super question. I don't have a super straight answer. So actually, depending on the detail of scene understanding you want to do, it is actually you need a quite good amount of computation power, way more, let's say, than a typical smartphone has. NVIDIA has, it's just an example, has like this automotive solutions where they have rather powerful GPU units that can be mounted, or that can be that can be assembled to the car and that can do some recognition. I can't give you any real strong quantitative answer here, but it's significant. On the other hand, if you think about Moore's law, and still we are like on the strong exponential growth of computation power, especially when you think about GPUs or TPUs, tensor processing units. So I think we will get at some point in a few years, we will have all the power, the computation power that we need to run a very detailed scene understanding. We will have it. If we have it now, depends on at which cost and also on at which power level. So think about when you have now a super heavy GPU like architecture that draws a lot of power, more than you might want to give in the current situation. Especially think about an electric car, like a battery-powered car, where you maybe don't want to spend a full kilowatt constantly just on the computing power, right? Like you want to be for sure in the area of low number of watts or something like that. Okay. Yeah, to monitor, that's also a good question. The second question, isn't it required to have some lights inside to monitor the driver? Yes, in the night it is. You will need, you can have an infrared light. Infrared light, why? Infrared light will not disturb the driver. The driver won't see it, at least if it's in the right frequency range, but the camera can see it. Actually, cameras can see infrared light. CCD sensors can see infrared light very easily, like way better than humans. Certain spectrums. I'm not talking about like telling you the temperature of the driver, but like in the near infrared, that works actually very good. Okay. Yeah. Okay. I think this is the questions that we have now. Okay, Alexander asks, what is the trends now in car systems developing, like cockpit, real-time system checks? No idea. I have actually no idea of this. I'm not working in this area, but if I understand the question right, reliability of those systems, testing, that is a really crucial thing. Like especially with the higher and higher levels of the autonomy, we need to make sure that the systems work, and they work like very, very reliably. So I think, for example, one of the bigger problems is maybe that's not really the electronic reliability, but the system cannot handle a situation and then switches back to a driver. And it's not so easy to have the driver in within 10 seconds to be ready to take over. And 10 seconds when you drive fast is a long time, right? Yeah. But sorry, Alexander, I don't have super. I don't have super precise like data on that. But actually, it would be very interesting to think about how to design the systems, and maybe even have system checks going on in certain intervals to make sure the system is up and running reliably, or having certain redundancy kind of measures. Redundancy that then would play back to the question before, that assume you want to have two units doing the whole deep learning in the car. It will draw potentially twice as much power, and electric power is a resource that you don't want to spend like overly easily, at least when it's super much, right? Okay. Okay, Camille asks, am I planning next webinars on that subject? With pleasure, I would like to go into different model architectures and into training, but that would be a series of lectures. So, like I said in the beginning, please check out the MIT and the Stanford computer vision courses. They are excellent. They're excellent materials. There are YouTube videos. There are slides to the lectures and YouTube videos, and you can learn a lot there. So they're actually, they have a lot of information. It's not little, right? Like you can spend 10, 20 hours listening to that stuff, and maybe you are not even like fully set in this moment. Actually, there's really a lot of information on deep learning on the web. That's a very nice thing of the YouTube and whatever video platforms, that now there's so much information freely available. All the talks from NIPS or stuff like this, maybe not all, but the most important talks are available. In general, it's actually becoming difficult to organize, to find, to stick just to the information that you want to look for. There's so much that you can spend your days just watching for that. So long story short, I have nothing like actually planned, but that might change all the time. Okay. Okay, so once again, thanks everyone for your attention. It was a pleasure. I like the topic and I like to talk about, and in case, try to shoot me a mail or a message whenever you find an occasion, and we can maybe discuss more. Okay, thanks so much. I'm stopping the screen share and give back to Ilya.
Okay, so now it's time that you can share your feedback with us, and we'll appreciate if you answer these questions. I see that most of you are very active here, so thank you for that. And thank you, Christian. Seems that we could think about to have a next topic which is more dedicated to one of the things that you talked today. And of course, I would like to ask everybody to don't stop to follow our social media channels like Facebook and LinkedIn, because we publish our plans about upcoming webinars, about recent news in the company. So if we organize an exhibition with you, you are more than welcome again to attend the session again. By the way, Christian, are you still here?
Yeah, go ahead.
Yeah, I saw that right now there is another question from Bartolomei Piotrowski, but I think that he's still here. How a car can navigate in a tunnel where there is no GPS range? Is SLAM or any other technique used then?
What is SLAM?
Wow.
Bartek, what is SLAM? So you have you have of course inertial sensors, right? That can still tell you where you are. So if you didn't lose GPS for overly long time, you can Kalman filter techniques. You get more or less where you are, right? Especially in the tunnel, you have also an idea that you can just follow the tunnel. I mean, navigating and driving the car, well, you need a rough idea of where you are. Like in a tunnel, I don't know. I don't know if the situation is already like rolled out anywhere in test that, For sure, like Waymo is testing in Phoenix. I'm not sure what is the situation there. I guess in the beginning you want to have as much kind of GPS contact as possible. It would be super interesting actually to get the different teams in Luxoft that are working on the different parts together to exchange like expertise here. So I'm definitely not a guy that is like super how to say, knowledgeable in car electronics or in embedded systems that are actually like used in the car. But that is a thing that would be super. I would be super like curious to know. I'm doing more on the cloud side, getting models there. partially on device side, doing modeling there, but I am, you know, I don't work on stuff that is really built fixed into the car, right? Like that's, you know, that's really already part of the car as it's produced, right? And that means that there are totally different constraints on and demands on stuff that is built into a car, like by the manufacturer. Okay, cool. Yeah, I think that the topic is super interesting, and yeah, even knowing what is going on here and there, that's already like a challenge. Iliana, do you, for example, know how many departments of Luxoft work in automotive? I mean, in auto I know, but I think there's much more, right? Much more.
Yeah, if we have to count them overall on the globe, there are more than 30 or 40 departments, I would say.
30 or 40 departments in automotive?
Yes, with the different projects. Yeah. Of course, these are very rough numbers, but we have to count them.
Okay.
I think that, Christian, we have to leave.
Yeah, I have to leave.
The topic is really interesting, so I believe that this is a good sign to continue thinking about similar webinars.
Yeah, definitely.
Good evening to everybody, and hope to see you again.
Okay.
Bye.
Bye, everyone. Thanks.
Bye.